All right, going on page 73 when we're done. Still talking about log functions. So as a reminder, because logs and exponentials are inverse functions, the characteristics have inverse relationships. We're switching x and y, right? Switch all the input characteristics with the output characteristics. So let's look at those. We have a logarithmic function. So here it is in general form. And in general form, it does include the a. So sometimes with general form, I'll say without any transformations. A technically is a transformation. That's your vertical dilation, a stretch or a compression. But when you do that, it doesn't change your where your asymptote is or what your domain and range are or your limit statements, anything like that. And b is greater than 0. But b being greater than 1 and b being between 0 and 1 give you two different graphs, which we'll talk about, just like they did for exponentials. And again, like we talked about yesterday, a and b are constants and can't be 0 or 1. Back up here at the top, let's say we're going to show exponentials. So we're just going to do a quick little sketch of a parent function. If I have y equals 2 to the x, it looks something like that, all right? And if I have y equals 1/2 to the x, it looks something like that. Okay, because I know that you are more familiar with exponentials. You're probably a little bit more comfortable with what they look like. We have exponential growth and exponential decay. There are other ways to get this to look like this. Basically, if I took this graph and reflected it in the y-axis, it would look like this, right? So this could be 2 to the negative x, and this could be 1/2 to the negative x. Like there's different ways to write them. And for both of these, we have horizontal asymptotes, okay? So knowing that, understanding that for exponentials can help us get what we need out of our little brains for logs, okay? So when you look at these log functions down here, because they are inverses, remember that you are reflecting in the line y equals x. So here, a is greater than 0, which means it's not negative, so I don't have a reflection. And b is greater than 1, like it is here. So if I take this and reflect it in the line y equals x, I get this one right here. If I take this and reflect it in the line y equals x, then I get this, but that's not exactly what this says here. So I'm going to give you some other information in terms of a's and b's, talk you through it. And when we do with actual numbers, it will make more sense to you, and then maybe the variables will end up making more sense. But here for the exponentials, your domain is negative infinity to infinity, right? All real numbers. Your range goes from 0 to infinity, and we don't include 0. For logs, those two things switch because they're inverses, right? That makes sense? Okay, good deal. So for this log function to look like this, it says that a is greater than 0 and b is greater than 1. If those things are true, totally works. Or another way is that if a is less than 0, which means I have a negative out there, so I'm going to have a reflection, and b is between 0 and 1. So basically, this only addresses if b is greater than 1, not something between 0 and 1. For this one, totally works if a is less than 0 and b is greater than 1, because all that changes from here to here then is a being negative, and if a is negative, I'm reflecting in the x-axis, that's why it would look like that. Totally works. Or a is greater than 0, a is positive, and b is between 0 and 1, meaning I have a fractional base there. But we'll look at some examples with those, but I do want you to have it in the generic variable sense. Okay, we're good? All right, so then we're going to talk about increasing and decreasing. Oh my goodness. And concave up, concave down. And if I'm talking about increasing and decreasing and concave up and concave down, what might I need to use and have written down? the fun chart, okay? So let's write down our fun chart. It's been a minute since we've done that. And I don't even remember why this came up. And I don't know if it was at the very end of last semester or at the beginning of this semester, but I was talking to somebody about something and they said, I still don't get that fun chart. Okay, if that is how you are feeling at this point, we've got to figure out a way to get you to understand the fun chart. So my plan in general, not just because of the fun chart, is to start having some review sessions, maybe once a week during math time, where you can choose to come for whatever it is, and maybe even after school, if there's enough people that will actually show up. So then you have to be honest about what you need to see. If you're like, you know what, that fun chart, it's always confused me, it still confuses me, then you need to be man or woman enough to say that and be like, I'm going to show up because somebody needs to explain this to me. And that way I can really make sure if you're not getting it, that you actually get it, in addition to other things that we go through. All right, anyway, back to this. Increasing and decreasing. So log functions are always increasing or always decreasing. They never switch. So since they never switch, when you switch from increasing to decreasing or vice versa, that's where you get your relative max and mins. So we have no relative extrema. And then there's a little note, unless it's on a closed interval, but that's a unique situation that we would talk about separately. So is this one here increasing or decreasing? Increasing, because as x goes from left to right, the y values are getting bigger. This one, as x goes from left to right, the y values are getting smaller, so it's decreasing. Since this function here is increasing the whole time, what does that tell you about the rate of change? It's positive. Since the function is increasing, the rate of change is positive. This function is decreasing, so the rate of change is negative. And if you use your pencil as the line that goes along the curve, like this, you can see that if this is my line, I know that that is a positive slope and that this is a negative slope. Okay, that's another way to look at it. So then we talk about concavity. So log functions are always concave up or always concave down. Okay, there's no change in there. Since there's no change in concavity, we have no points of inflection. Is this one concave up or concave down? Down. So the rate of change is decreasing. The rate of, is this concave up or down? Up. And so the rate of change is increasing. So this function is decreasing, but the rate of change is increasing. Make sense? We good? Questions? All right. And I know when we first started doing all that, all those words about increasing and decreasing the rate of change, it like got all muddled in your little brains and really stressed some of you out. But I think over time, most of us have kind of gotten to feel a little bit better about that, and it might not be everybody. So I will get you there, I promise. Okay, end behavior. So for log functions in general form, that form up there where the only transformation I possibly have is the a, as the input values increase without bound. If it's increasing without bound, what does that mean? Where are we going? Infinity, okay? As x goes to infinity is what that is saying. So for both of these, as x goes to infinity, my y is going either to infinity or negative infinity. So the output values will increase or decrease without bound. It's my only option there. Then since the logarithmic functions have a restricted domain, so up here, my exponentials had a restricted range. Domain was all real numbers. So I have a restricted domain. This horizontal asymptote that I had right here changes to a vertical asymptote for these because it reflects as well. Right? So since logarithmic functions have a restricted domain, they are vertically asymptotic. Okay, if you didn't like multiplicatively and exponentiation, now we have asymptotic. All that means is it has an asymptote. It's just a different form of the word asymptote. That's all it is. So it means I have a vertical asymptote at x equals 0 before I move anything. And as a result, the left-in behavior occurs at 0, not at negative infinity. I can't say as x approaches negative infinity because it will not. It will approach 0, but only from the right. Okay, so here are my limit statements. The limit as x approaches 0 from the right, that's what's happening here because that's where my boundary is either going to be infinity or negative infinity. I do get to go to infinity, and that answer there is also either positive or negative infinity, depending on what's happening. Okay, what questions you got? We all good so far? All right, so let's write our limit statements. Now, overall, y'all have been doing a phenomenal job of writing your limit statements. Yes, you will have lots of multiple choice questions like that, but you will have to actually write it out on the AP exam, and it being in perfect notation matters for you to get your credit. But you're doing a good job, so just don't get sloppy. So my left in behavior, remember I have an asymptote here. So I'm going to say the limit as x approaches 0 from the right, that little plus sign up in the where the exponent goes, of f of x equals and negative infinity. Good. And then the limit as x approaches, and I do get to go to infinity on the right-hand side, of f of x equals what? Infinity. Good. Everybody okay with that? Any questions? All right, you write out your limit statements for the next one. And don't be a Melissa. Okay. That's what I got. Y'all agree with that? And we used h of x? Yes, very careful with that. All righty, so then on C, I mean, you could think through it just as an equation, but I think a picture helps a lot. So just like for your generic exponential, looks like that, right? That's your exponential. And that's when your base is greater than 1, 2 to the x, 5 to the x, whatever. So if you need to think about that one first, that's fine. If not, if you know your generic log looks like this, where your base is greater than 1, that helps a lot. Because here, my base is greater than 1, it's 3. So I should start off like this. Then this 2, all that is a vertical dilation. It would stretch by 2. But stretching vertically is not going to change where my asymptote is. It's not going to change anything else. So since I don't really have any like tick marks on there anyway, that's what it looks like. And my asymptote's there, which you can draw in. You don't necessarily have to. I just want to make sure you know where it is because it matters. Okay. So my left in be actually, then you should be able to write that out. Once you get the picture, writing it out is easy enough. Right, Melvin? Okay, so this would be negative infinity and infinity. Okay, we good with that? Yes? All right, we should be semi-experts at limits. I think that that's one thing that we pretty much all have down. Okay, so here we need to determine if the log function is increasing, decreasing, concave up, concave down. So for A, concave up or down? Up. It's up like a cup, right? But it won't actually hold any water, but it doesn't have to. I think you still get it. Is the function increasing or decreasing? Decreasing. All right, since the function is concave up, what's happening with the rate of change? It's increasing. Since the function is decreasing, the rate of change is negative. And that's where your fun chart comes in. If you know it without the fun chart, great. If you don't, write down your fun chart so you can get it off of there, right? Here's my fun chart. Okay, so look at B, concave up or down? Down. And since it's concave down, what's true about the rate of change? Concave down, rate of change is decreasing. Is the function increasing or decreasing? Increasing. Since the function is increasing, what's true about the rate of change? It's positive. Okay, we good? All right, now on C, it would help greatly to have a picture. So ignoring the -4, just the log base 6, I know that looks something like that, okay? But a whole lot better. The 4 won't really change what it looks like since I'm not really sketching it out perfectly, but that negative reflects it in which axis? The X, good. Reflect in the X axis, so it ends up looking like that. And so since I can draw that, I could write my limit statements if I needed to, but they're not asking me to. Or I can talk about my concavity. Is it concave up or down? Up. So what's true about the rate of change? Concave up means the rate of change is increasing. Concave up means it's increasing. The function, is the function increasing or decreasing? Decreasing. Function is decreasing, so the rate of change is negative. Decreasing is negative. Okay, you see where that's coming from? Yes? Questions? Any questions at all? We sure? Because I heard a whole lot of crazy stuff out there. We good? Oh, okay. All right. Let's look at example 3. Selected values of several log functions are shown in the tables below. For each table, find the value of the constant k. Do I need to figure out whether or not these are logarithmic? No. It says the values of several logarithmic functions. Like it's straight up telling me these are log functions. So the answer isn't yes or no here. They are log functions. I should know how log functions work so that I can figure this out. So even though I know they're log functions, I don't get to treat my input values the way I understand unless my output values are equal length intervals, right? And just because they're logs doesn't mean that the information they gave me is equally spaced. So I'm going to look over here to double check. Each time I'm adding 1, which means I have equal length output value intervals, right? Since I have equal length output value intervals, that means my input values most likely are changing multiplicatively, right? So to get from here to here or here to here, what am I multiplying by? 2. So what does k equal? 4. Okay. We okay with that? So on the next one, I'm going to look first at my output values. I'm adding 5 each time. So since I have equal length output value intervals, I can go look at my inputs the way I understand. And it looks like I'm multiplying by what? 3. So what would k be? 2. Okay. Everybody okay with that? We good so far? Okay. So over here, looks like I'm subtracting 10, but we talk about it as adding a -10, okay? Equal length output value intervals. What are my input values being multiplied by? Are they being multiplied by the same number over and over again? No, because look here. If I do 18 over 6 and 54 over 18, I get the same number, right? I get 3. Or 16 over 8 and 2 over 1. If I put 5 over 4 and 7 over 5, not getting the same number. But I know it's a log function because it told me it's a log function. So if you recall when we were doing this with exponentials, we got to some where we had equal length input values, but the output values didn't look like they were doubling or tripling or anything because there was some sort of transformation within it, okay? So what we did was our differences first, then found the ratio. So that's what we're going to do here. I've got, when I find the difference, 5 minus 4 is 1. 7 minus 5 is 2. which doesn't necessarily mean that it's doubling, but maybe it is. You can kind of figure it out from there. These differences here are k minus 7 and 19 minus k. Does that make sense to you? So I can set up a proportion. Just like over here, I can put 8 over 16 has to equal 2 over 1, right? I can start with 2 over 1 has to equal k minus 7 over 2. Do you understand where that's coming from? And then when I multiply, 2 times 2 is 4, I get 4 equals k minus 7. So what does k equal? 11, right? Makes this 11. Right? You can use some reasoning skills within there too. You wouldn't necessarily have to do the math there, but depends on how much you actually understand it. Okay? Questions about this? Okay. Now let's look at this last one. Looks like I am adding 7 to my output values. If I need to figure out, like I know when we look at these, you can just tell, oh, I'm multiplying by 3. But don't forget that the way you actually find what you're multiplying by is to take 18 over 6 or 54 over 18. So if you don't just automatically know what you're multiplying by here, I'm going to look at these two and see if maybe even they're the same. If I put e to the 10th over e to the 7th, what does that give me? E to the 3rd, right? That's the way exponents work. And if I take these two and I put e to the 1st over e to the negative 2nd, what does that give me? E to the 3rd. So I am multiplying by the same thing every time. I'm multiplying by e to the 3rd. So if I take e and multiply it by e to the 3rd, what do I get? E to the 4th. That's my answer. Don't let the e's freak you out. It's basic exponent rules, regardless of whether it's e or x or whatever it is. What questions we got? All right, good deal. So now we're going to find domain and range of the following log functions and write limit statements. So for all 3 of these, the base of the log is greater than 1. So for all 3 of them, the original parent function looks like that. Okay? And whether you have it written down or it's just in your brain, whatever, that's what it looks like. So for this one here, log base 3 of x. So the log base 3 of x part is basically just exactly that. This, too, all it is a vertical stretch, so it doesn't really change the way my picture looks because I don't have a scale. And here is my asymptote. My asymptote didn't move anywhere. So where does my domain start? 0. Do I include it? No. And I'm going to infinity. My range, negative infinity to infinity. Then by now, these limit statements should be a piece of cake. Limit as x approaches what? 0 from the right of f of x equals what? Negative infinity. Good. And then the limit as x approaches infinity of f of x equals what? Infinity. Any questions about that? We good on those? Or on that one? Okay. So now here, the log base 2 of x looks like that little thing over there. What does this 3 tell me I do? Transformation-wise. Move to the right 3, okay? So since I'm going to move the whole thing to the right 3, the asymptote that was at 0 moves over to the right to 3. Okay? So that's now where my asymptote is. Then the 5 itself really won't change anything because it stretches, but I don't care. But that negative reflects it in what? The x-axis. So then it means it's going to look like that. So where does my domain start? At 3, Do I include it? No. And we're going to infinity. Range is the same. Right. Then go ahead and write out your limit statements. For the left one, it's the limit as x approaches what? 3 from the right. Very good. Any questions at all? All right. Now on this one, this 3 does not mean that I go to the left 3. This 3 does mean that I go to the right 3. But if I'm going to look inside of here and decide what those numbers are telling me to do, then this right here needs to be factored out. Since this is 1, I had nothing to factor out. But this isn't factored enough. So I would have to rewrite it as h of x equals 8 times the log of 2 times x plus, I'm going to rewrite that because I'm running out of room. I didn't write anything wrong though, I'm just rewriting the same thing. 8 times the log of x times, no, not x, good Lord. 2 times x plus what? What number would it have to be? 3 over 2? Because when I multiply it back, I got to get that back. So now that I have it factored out, I can look at this as my horizontal compression and this as my translation. So that means I go to the left 3 halves. 3 halves is like 1.5. So it's right here. Okay. The 2, which is the horizontal compression, squishes things together, but it doesn't move anything, and I'm not being exact with my numbers anyway. And then the 8 stretches it, but really all I care about right now are the horizontal translations and the reflections. So, but I am going to try and at least graph it semi-accurately on these little hash marks because they're there. I know that like here, this is going through 1, right? And since this was at 3, this goes through 4. Since this is at -3 halves, it's going to actually go through like -1/2 right here and look something like that. Which you're not graphing it for anybody but yourself, so you don't have to. I just want you to at least think about that. So where does my domain start? -3 halves. Well, my board's being weird. -3 halves, go into infinity. Range is the same. And then hopefully you should be able to write out your limit statements. What's it called? H of x. Oh, I guess I still need to see it, don't I? Equals infinity. All right. Any questions at all? We all good? Yes? Okay. Grab your other sheet of paper. We're not doing everything on this paper, but we are going to talk about some of them. So on example 5 here, they give us graphs of logs and we're supposed to match them. So I'm going to ignore the actual pictures for a while, and we're going to go through and look at these equations and just draw all of our own pictures, and then we'll worry about matching them up. So, and these first 3 all are like log base 2. So I know just a plain old log base 2 of x, since that's greater than 1, is going to look something like that. Okay. Then the only difference between G and F is that I have that negative x. If x is negative, what do y reflect in? Y. So if I take this and reflect it in the y-axis, it's going to look like that. Okay. then the only difference between H and F is that the negative is out front. If the negative's out front, what do I reflect in? X. So I'm going to take this and reflect it in the x-axis, and it looks like that. Okay, does that make sense? You see how to just quickly get those little pictures. All right, so for K, the base is different. So if I'm going to ignore that negative x for a minute. If I just have log base 1/2, that means it starts off looking like that. Then this negative reflects it in which axis? Y. So that means it's going to end up looking like this. And this is the one that we're using here. Okay. So you understanding visually what's happening can help you with lots of things. I could write my limit statements here if I needed to, but I can definitely go match this up now. F goes with which letter? C. What does G go with? A. What does H go with? B. And that means K goes with D. So I highly suggest you try and get things out of your brain before you just start trying to match them up and doing stuff even when nobody's making you, and not just trying to stare at a graph and figure it out that way. Okay, we good on that? All right, so let's look at example 6. It says, given the function, determine the asymptotes and the end behaviors, use limit notation. So we're not going to write any more limits. I think we've written enough of them. I think if you have a picture, you can write them. But I do want to look at these pictures. So all 4 of these, the log is base what? 10. So if it's log base 10, my parent function looks like that. Okay. So this 1 right here means I do what? Which way do I go? The right. If I go to the right one, then here's my asymptote. That's the only difference between these two. So that means the rest of it looks like that. And my vertical asymptote is at x equals 1. It is not at 1. It is at x equals 1 because it is in line. We write the equation of the line. Okay. And then from that, I think you could write your limit statements. Again, I'm just not going to make you write them over and over again. We good on that? All right. So then here, what does this 2 mean that I do? Go to the left 2. So if I go to the left 2, so does my asymptote because it's vertical. And then that's the only difference. So it looks like that. So my vertical asymptote is at x equals what? -2. Now on C, when the transformations are written this way, regardless of whether it's a log, a quadratic, whatever, it seems to like make some of your brains just freeze, or you make stuff up, which some of y'all are really good at. We have to really just start learning not to make stuff up. But it's because it's in a different order than you usually see it. So something I think is helpful is for you to rewrite it in the order that makes more sense in your brain. And that would be that and you'll see it like this a lot when there's a negative out front. It's just the way we write things sometimes. But if I rewrite it as y equals negative log of x plus 4 plus 2, then I think it's very easy for you to see that that 2, what is that 2 doing, Melvin? What does this mean is happening? Somebody want to help him? It's going up 2, okay? Where when it's out front out here, that throws y'all off sometimes, okay? Which is, I mean, I get why it throws you off. But if you put it in the, just rewrite it and know that nobody's making up something new, you know how to do it, okay? So with all that said, then this 4, what does that 4 mean that I do? Left 4. So here's my asymptote, right? And then the negative means that I'm going to reflect in which axis? X, so it's going to go like this. The 2 means that I go up 2. Now, so it will change my x-intercept, but nobody's asking me for it. And this is just a quick sketch, so it doesn't even have to be perfect. But I'm going to show you what would actually happen to it. So basically, it's not going to go through right here because we're going up 2. It would go through this point right there, and it would look something like that. But again, we don't have to be perfect about it. just want to at least throw it out there. That's enough to tell me that my vertical asymptote is at x equals -4. Okay. We good so far? All right. Do I move left or right at all here? No. So my asymptote stays right there. I do move up, or I'm sorry, down 3, but again, it really doesn't matter if I don't have a scale, so it just looks like that. So my vertical asymptote is at x equals what? 0. Everybody okay with that? Okay. So we're not going to do the bottom. I just didn't bother taking it off. I probably could have done without this whole page, but I wanted you to see some of the other graphs there.